Okay, well, thank you very much, and it's indeed an honor to be here. And I must say that Al Romig would rather be here himself, but unfortunately his mother passed away a couple days ago, and so Al asked me if I could stand and give this presentation. So I said, Al, do you have any comments or slides that you'd like me to show? And he says, no, use your own personal experience and go with what you know. So I said, let me try to understand this. I have to talk about the last 50 years of materials and the next 50 in 10 minutes? And he says, yes. So I asked Lance, could I have even a couple more minutes? And he said, no, just go ahead and work it out. So here it goes. So it is very challenging indeed to foresee like 50 years into the future in materials, but if the past is a prologue, the future of materials will be quite exciting. And I'll give a few hints of what the possibilities are. My business, has been aircraft engines for a long time, and when I think back to 50 years ago, of course I was still undergraduate then at Case Tech, but 50 years ago in my company, the big activity was developing a new class of engines for the C5 program that the Air Force had just started. So that was the first wide-body transport type airplane of its time. The engine was developed was called a TF-39 and ended up being quite a successful engine, still flying today in many C5s. But the commercial derivative of that became the CF6 engine, which many of you, probably all of you, have flown on airplanes powered by the CF6. It's in the 747, the 767, the Airbus 300, 310, et cetera, those series, over 1 billion flight hours. The big breakthrough with that engine was a 25% improvement in fuel efficiency over past engines, and that was due in part to a new change in engine architecture to be a high bypass engine, but also the implementation of a lot of new materials. So let me see if I can, beat me to it to get the slide. So if you notice, by the corner of 1960 there, that was the advent of the engines with the bypass ratio. And if you can, and you notice there's been big incremental improvements in fuel efficiency when we changed the engine architecture. If you just take the average of fuel efficiency, which is a key metric in our business, of course safety, would be the #1 metric. And we also have made great improvements in safety at the same time as we've improved fuel efficiency. But when I talk to the design engineers and say, what is the proportion of that improvement that was due to materials as opposed to other changes in engineering, their estimate is 1/3 to 1/2. So I'll accept the 1/2 as being a pretty good estimate. I noticed too, though, if you notice about a 1% improvement year after year of improvement in fuel efficiency. For the next 50 years, that says the engine will generate fuel. So I think that's one of the big challenges for the future. These engines use the Brayton cycle in thermodynamics, which tells you want to have a compression ratio as you possibly can and as high a burning temperature to power the turbine. So there definitely are limits on practically what you could do there, and most of those limits are due from a material standpoint. And by the way, in our modern engines, I don't know if you realize, the gas pass temperature in a turbine is several hundred degrees above the melting point of the nickel superalloy that the turbine blades, et cetera, are made from. And so what we do is we fool the metal to think it's cooler by essentially that turbine blade is a radiator with a lot of internal cooling passages. Plus we put some cooling air on the surface, and then there's an insulating layer of ceramic. So designing, developing new turbine blade alloys is really, really hard. And we reach a limit on what could be possible. We look to the future, we say, well, maybe we should make these out of ceramic materials that could have a much higher operating temperature. And we've begun to do that already. And the new LEAP engine be introduced in service in a couple of years would be the first application of ceramic matrix composites in the turbine section of an engine. But it will not be on a rotating part. It would be on a turbine shroud where the blade tips, they rub against the shroud. So with that background, at least turbine engine-wise, we could say, what do we see the real improvements for the future are? In one thing would be the Brayton cycle will probably go by the wayside, within 50 years. And there's a lot of concepts for new engine cycles that would be more efficient. One of the intriguing ones would be to have a number of small fans along the leading edge of the wing of the airplane, and each fan would be powered by electricity that's conducted by a wire of superconductivity type of a material, so you'd have low loss, and you'd have a turbine engine that essentially would be an electrical power generator. And there's other kinds of exotic ideas like that. So I think within 50 years, we'll know what the answer is. Nonetheless, regardless of what new configuration of the engine is, there will be significant challenges in materials. As we look to the future, though, what I have to say is one area that materials has fallen short in the past has been the long time it takes us to do a development. And so historically, if we go with a new class of material, like an intermetallic or even a ceramic matrix composite, the development time is easily 20, more like 30 years. An example in our business is titanium aluminides, which actually program started in the Air Force in the 70s, and only within the last several years have we implemented turbine blades made from titanium aluminides. Now, they had great promise even 30 years ago because they were equivalent strength of nickel alloys and they had half the weight. And so tremendous payoff in an engine, but there are a lot of other technologies had to be developed and we had to have the industrial capability to make the material on a large scale. So that historically, it takes 20 to 30 years to do a new material. For the future, that will not be true. What I foresee will be able to do development in 1/3 the time. And not only in structural type materials like I've been talking about, but I think across the board. And what gives me the hope would be, first of all, some personal experience that we've had in doing accelerated programs, of course they're on a selective basis, but for the first time ever in the industry, we developed a new turbine blade alloy and qualified it for flight with the FAA within 2 years of starting the program. Now, normally that would have been at least a 6-year program. And what we did is we used some computational tools, and importantly, because it was such a key project for our business, we had an integrated team with the design people and the manufacturing people, and it worked, and it kind of gives us a roadmap for the future, what we can do in other areas of materials, kind of following the same sort of recipe. So I think in materials, rather than trying to pick, what will be the big winners in the next 50 years or plus, what I think the big winner is going to be finding a way to develop these computational models and work together as an enterprise which would include partnering with the supply chain folks, with university and governments, with the government labs, to find ways to select the right material to focus on and then rapidly scale it up into an application of interest, and then you would be off and running. Let's see, this next chart, though, shows, let's see, how do I, this next chart shows what oftentimes has happened in the past, one of the reasons why it's taken us so long to do a materials development, and you've heard of the Valley of Death. Well, what happens is, on the left side, the materials folks, they think they know the right answer, but they really don't have the buy-in or the support from all the other stakeholders and the decision makers. And so it's almost an adversarial type of relationship, and for good reason, because a lot is at stake. You know, aircraft engines cost us $1 to $2 billion, for example, to develop a new engine, and if you have a field problem, it could easily cost in the hundreds of millions of dollars, you know, to solve that problem. So you got to make sure whatever change you make, you know, that you're absolutely right. But what we've learned is you don't have to accept that way of doing business. And so this approach, which is what we've managed to do on a selective basis, you know, is much better. And so we work as collaborative teams, and we're well integrated. And what we should have in mind is to do this approach as ordinary type business rather than on the special case on urgent problems, you know, that arise. Key to being able to have an accelerated program, though, is also being sure that you're right. And so we need computational models which are fairly good at predicting what will happen. We need the understanding, say from a more basic science standpoint, of what the degradation modes of these materials would be in the application environment. And we need very smart ways to test these materials, which is beyond some of the old standard tests that we have done, which turns out are not terribly useful in the kinds of high temperatures, high pressure environments, you know, that we encounter now. We heard yesterday from Eric Schmidt that the key role that government has had in stimulating the new innovation, and this has certainly been the case in computational type materials, in also building new characterization type facilities for materials. So going forward, I think a coordinated effort by industry, government, and universities, which will no doubt happen in the next 50 years, will be essential to accelerate the development of materials, you know, across all the different spectrums of interest. And the reason I say certainly because there's already some of that, you know, has happened. Now, what I have one last slide to show, and this is from my old job at GE, where I actually plotted the work that we did internally on developing models. And you can see in some of these, by the way, are models that you can also purchase. But a lot are ones that we built ourselves. So starting around the mid-'80s, you know, we kind of focused on process models and more of a reactive use to help us solve problems that we were having, either at a supplier or problems that we were having in synthesizing some of the new materials that we wanted to develop. And these got further extended into predicting the microstructure of the materials. And then if we have a good idea what the microstructure would be, we can predict the properties. And so as we've gone forward, this slide's a little misleading in the sense it looked like we stopped working on process models, but that's not true. We continue to work on process models and structure models and property models in real time. And probably now we have 60, 70 models that, you know, that we currently use in my business to go help us advance the development of materials. And a lot of these are in the composite area, I should say. So you know, it's not just metals that we're interested, though what we show here are some of the examples of metals. Another thing about the shape of this curve, it's not linear, it's exponential. And I can only imagine 50 years from now what this curve would look like. You know, I expect there'll be many hundreds of models here. So therefore, what I'd say is we need a collaborative ecosystem, not only for the experts to work together on solving these problems and developing these materials and quickly finding ways to integrate that to solve problems or satisfy needs, but we also need the computational type environment that would be a facilitator for the collaboration. And that's something, there's a couple elements of that floating around, but I think we're not there at the right answer, but it's certainly within time we have this meeting again in 50 years, that'll be a solved problem. So in conclusion, what I'd say, the future for materials is quite exciting, and regardless of what field of materials that one is interested in. I think we have a pathway to change the paradigm for long development times of materials, and fully integrate with the others in the engineering disciplines that we work with. And at the end of the day, I'd say the challenge is there because after all, that everything physical is made from some type of a material. So we have tremendous opportunity, you know, to influence the engineering world. Okay, so thank you very much.